learned a lot about skeletal muscle tissue, how it's striated and contracts using the actin-myosin sliding filament dance you've heard so much about. Your cardiac muscle is also striated and uses sliding filaments to contract, but the similarities end there. For one, their cells look pretty different. Skeletal muscle tissue has long multinucleate cells, while cardiac cells are squat, branched out, and interconnected, each one with one or two central nuclei. The cells are separated by a loose matrix of connective tissue called the endomysium, which is chock full of capillaries to serve up a constant supply of oxygen. Cardiac cells are also loaded with energy-generating mitochondria. In fact, mitochondria take up as much as 25 to 35% of each cell. Skeletal muscle fibers are both structurally and functionally separate from each other, meaning that some cells can work while others don't. That's why you can grasp a delicate flower with the same hand that you can use to crush a soda can. Cardiac cells, on the other hand, are both physically and electrically connected all of the time. It takes precise coordination to create the high and low pressures required to pump your blood, after all, and cardiac cells need to be linked in order to have that perfect timing. And there's one more thing you need to know about your heart cells. Some of them can generate their own electricity. How in the name of Raymond de Vusens can that be? Well, rewind your brain to when we explored the electrical marvel that is the action potential and how it triggers both neurons and muscle cells. That process started by depolarizing the cell, that is, pushing the cell's membrane potential from negative toward positive past a threshold that triggered voltage-gated ion channels to open. These are your pacemaker cells. Pacemaker cells are what keep your heart beating at the correct rhythm and ensure that each cardiac muscle cell contracts in coordination with the others, because you